Hey math fans, Alex here, and coming to you live from a brand new apartment in Florida. All right, so last time got a little complex, pun intended, but this time we're going to talk more about the characteristics of characteristic functions. Okay, so the first thing is to kind of recall that for generating functions, we had a couple of properties. So for generating functions, a x of z, where z is complex, we had the following. We had that the expected value of the random variable was just the first derivative of the generating function evaluated at 1. And we also got that the variance was a little stranger, but not too bad, right? It's going to involve a second derivative plus the first derivative evaluated at 1 minus the first derivative evaluated at 1 squared. Okay, this might be a little complicated, but for characteristic functions, we're essentially going to derive a couple of similar properties if you want to find the expected value in the variance. Because like I said, you're not always going to have a PDF, but you are always going to have a characteristic function. Okay, so let's go ahead and start. Okay, so for characteristic functions, I want us to note something. Okay, so remember that we're noting e to the itx, okay? And if you'll recall what a characteristic function even is, the characteristic function is actually just going to be the expected value of e to the itx, okay? So what is e to the itx? Well, without the I, you could expand that in a power series, and it turns out that for complex numbers, you can do pretty much the exact same thing, okay? So I'm not assuming that you've taken complex analysis, of course, just like kind of in the last episode, but here we're just going to go ahead and make the assumption that it works the same way, and you can take my word for it. So this is going to be the infinite sum from k equals 0 to infinity of the quantity, the exponent right here, itk, well, it'd actually be itx to the k all over k factorial. Okay, and let's just expand this out and let's see what we get. So this is equal to what? Well, if k equals 0, then that's going to be something to the 0th power over 0 factorial, which is 1. Plus, if k equals 1, that's just going to get us itx to the first power over 1 factorial. Might as well just write that out. Plus itx to the second power over 2 factorial, plus, and we'll do one more, itx to the third power over 3 factorial, and so on and so forth. But remember that properties of the imaginary number I kind of can come in clutch here, and we get what? Well, the first term is 1. The second term is just going to be itx divided by 1, which is just itx. Now we're squaring the I, the t, and the x. So when you square I, remember again that I squared is equal to -1. So we're actually going to be subtracting t squared, x squared, all over 2 factorial, which is 2 times 1, or 2. Okay. Plus I cubed, t cubed, x cubed. Okay, but remember that I cubed would just be I squared times I, which is -1 times I. Okay. So we could say that this is equal to a minus I t cubed, x cubed, all over 3 factorial, which is 6. This minus sign's a little uneven. Okay, and so on and so forth. I to the fourth is 1, so the next term is going to be a positive, but nonetheless, you can kind of expand it like this, and what we're going to do to find the characteristic function is just take the expected value of both sides. Okay, so we know that fx of t is just the expected value of e to the itx, which implies fx of t is just going to be the expected value of all of this. Okay, so I might as well do that in this color. 1 plus itx minus half t squared x squared minus a sixth I t cubed x cubed, and so on and so forth. Okay. And then remember that with the expected value operator, we can actually just distribute that. Expected value of a sum is the sum of the expected values. Okay, so this is really just going to be the expected value of 1 plus the expected value of itx plus the expected value of minus 1/2 t squared x squared plus the expected value of minus 1/6 I t cubed x cubed, plus and so on and so forth. Let's actually figure out what this is. Well, the expected value of a constant is just that constant. And then from these other ones, keep in mind that we can pull out everything that's not related to x, because everything not related to x is a constant. Okay, so we can pull the I and the t out. Here we can pull all of this junk out. And same for that. Okay, so what we're going to get is that this is going to be 1 plus it times the expected value of x, which is what we're wanting, minus 1/2 t squared times the expected value of x squared, minus 1/6 I t cubed times the expected value of x cubed, and so on and so forth. Okay. Now, how do we get the expected value of x by itself? Okay, we want this by itself. Any ideas of what we can do to the characteristic function to essentially negate all other terms? It's going to be similar to what we did with generating functions. It's going to involve some derivatives. Okay. Well, what we want is we want to get rid of the t, right? So we're going to get rid of t by differentiating once. Differentiating once. Okay, and I'll save the rest of this for a minute. Let's go ahead and differentiate this once, and what we're going to get is we're going to get 0 plus I times the expected value of x minus minus t times the expected value of x squared minus who cares, it's going to be some t squared expected value of x cubed plus dot dot dot. And I want to get rid of everything except this term. Well, it's a characteristic function, so I get to plug in a value of t. What value of t makes everything else go to 0 except 0? Okay, so after differentiating once, then we're just going to plug in t equals 0. And setting t equals 0. So then what we get is we get that I times the expected value of x, I times the expected value of x is going to be what you get when you take the first derivative of the characteristic function and evaluate that at 0. Okay. But again, how do I get the expected value of x by itself? Well, there's a neat kind of trick. What you do is you multiply both sides by negative I. Because I squared is negative 1, negative I squared is negative negative 1, which is a positive 1. Okay, so that's going to go ahead and imply, that the expected value of x is negative I times the first derivative of the characteristic function evaluated at 0. Okay. Okay. Now, to find the variance, we're going to just do it from the definition. But in order to do that, we're going to need to find the expected value of x squared. How are we going to do that? We're going to kind of do it the same exact thing. We're going to do the same exact thing, right? We're going to differentiate twice. And that's going to get rid of those terms. And this is going to come out pretty clean. It's not going to be any I to worry about. So let's just see what we get. So to get the expected value of x squared, let's try differentiating twice. And again, setting t equal to 0. Okay, so maybe I should highlight this in a different color. Oops. Okay, so we want this and we want that. Okay. So what do we get when we do that? Well, we already kind of differentiated this once. When we differentiate it twice, like I said, these first two terms kind of go to 0. What's this differentiated twice? Well, if you differentiate it once, you're going to get a minus t times the expected value of x squared. Differentiating it again, you just get a minus 1, right? Because the derivative of minus t is just minus 1. So this is going to end up being minus the expected value of x squared. And you're going to have a bunch of other terms, right? But when you differentiate twice, every subsequent term is going to have a t in it. So when you plug in t equals 0, those just immediately cancel. And you get that minus the expected value of x squared is what you get when you differentiate twice and plug in t equals 0. Okay, so then it's pretty obvious to see that this implies that the expected value of x squared is equal to negative the second derivative of the characteristic function evaluated at 0, and thus the variance of x, which remember the variance by definition is this minus the square of this, would have to get us minus fx second derivative evaluated at 0 minus this thing squared. Okay, so let's just put it in parentheses for now. Okay, but what do you get when you take a minus squared? Well, you get a positive. I squared is a negative 1, though, which is going to cancel with this negative. So this is actually a positive. Positive, and then first derivative characteristic function evaluated at 0, quantity squared. Okay, so that is the formula for the variance if you're given the characteristic function. Okay, now we're going to do a couple of examples, and that's going to kind of end this video off in this section. Okay, so we're going to look at two examples. We're actually going to look at the same two examples that we looked at when we found the characteristic function of a discrete and continuous random variable. So we're going to start off with the Poisson distribution. Okay, and the thing to note is that we already found the characteristic function of this, so I'm just going to give that to you. You can, of course, find it very easily from the definition. Just look back to the other video. That was e to the lambda times e to the it minus 1. Okay. So basically what it comes down to is, show that the expected value of x is lambda, and the variance of x is also lambda. If you think about it, it's just a Calc 1 exercise, because we have kind of the forms. The only tricky part is that with the expected value, there is a minus I involved. Let's go ahead and do that. So, do it in blue. So first of all, let's just take the derivative of the characteristic function, because we know we're going to have to do that anyway. Okay, so the first derivative of the characteristic function, well, what's the derivative of e to the something? Well, that's going to be e to that something times the derivative of that something. Well, lambda is a constant, so that can come out. So we really only have to worry about the derivative of this. I know I didn't talk about the derivative of e to the it, okay, but hopefully you see that I is a constant. So that's really just going to be I e to the it. We are treating I like a real number, even though it is imaginary. I'm telling you it works the same way. This is an analytic function. Just take my word for it. And then the derivative of the minus 1 is 0, so that's why I didn't include it. Okay, so I believe that is the first derivative, and then to find the expected value, we need to evaluate that at t equals 0. Okay, so fx prime evaluated at 0 would just get us e to the lambda times e to the I times 0, that's e to the 0, minus 1 times lambda times I, e to the 0. Well, e to the 0 is 1. 1 minus 1 is 0. 0 times lambda is 0. E to the 0 is 1. So this is going to end up just being 1 from this term, right? This term is 1 times lambda times I times another 1. Okay? So then the expected value, based on what we just proved, is going to be minus I times this first derivative, which is going to be minus I times lambda I. But remember, minus I times I is just 1, positive 1. So those kind of cancel, and we get lambda. Okay? Okay. Now, as far as the variance goes, variance, I'm going to leave to you as an exercise. You already know what the expected value of x is. We just kind of showed that, so please go ahead and use that, and you just have to find the expected value of x squared, okay? Which is going to end up being, I believe, lambda squared plus lambda. So that's what you have to show when all is said and done. Okay? So let's look at one more example. That's the normal distribution. Trust me, this is not going to be as hard as proving what the characteristic function of the normal distribution was. I'm just going to give that to you, because at this point, I already proved it, so it's fair game to use. Okay, so the characteristic function of the normal distribution wasn't that hard. It just took a long time to prove an integral. It's e to the minus t squared over 2. Okay, so what are we trying to do? Well, remember that this is, I keep forgetting, standard normal. So we have to show that the average of the standard normal distribution is 0, and the variance was 1. So again, we're going to do the same thing. Take a derivative, set it equal, or plug in 0. Fx prime of t is equal to what? Well, it's going to be e to the minus t squared over 2 times the derivative of this. okay, which is minus t. So then plugging in 0, that immediately gets you 0, right? Zero times who cares, you get 0. Now, we're not done, because remember that the expected value of x was minus I times the first derivative evaluated at 0, which is minus I times 0, which is 0. Okay? And again, the variance, I'm going to go ahead and leave that to you as an exercise, but use this first derivative and differentiate it again. Okay? And then again, use the property that the variance of x is just expected value of x squared minus the expected value of x squared, which is 0, so really you don't have to worry about that. Okay, so I will leave that to you as an exercise. That's it for this section. That's characteristics functions, which are going to be really, really important in the proof of the central limit theorem, which we're going to discuss in the next section. So thank you so much for watching. I hope the quality of the audio is okay. I'm kind of in a more reverberated environment, more of a reverberated space, so hopefully you can hear everything okay. And I'll see you in the next video. Have a great rest of your day.